Okay, I guess we're going to be slowly starting in. Let's see if starting out. It's always, I mean, I need to like have like a proper routine for checking things like in the beginning, but yeah, but I guess we are live, so it looks good. And welcome everybody for for this like a second time when we're doing it online. So what started basically as like a meetup, in Munich here in Germany, and now it's going like all the way to online. But as I said, also like on Twitter today, is that it's pretty exciting that it's actually allowing us to have speakers also like very international ones. And today I'm like super happy to have Leigh, who is based like in sunny California, and actually having even different like times. So for us it's evening, and for her it's like early morning, and she's going to be talking about amazing things with machine learning and hardware. But just a couple of words for maybe those of you who found it not from the meetup, but maybe from Twitter. We use Meetup still as a kind of like a bit of like a legacy setup, right, in order to communicate our next event. So in order for you to know what next event is going to be and when is it going to be, feel free to sign up for our Meetup page. We also have this Slack channel that the idea is that you didn't just like have it like every month or like bi-monthly one event, right? But you also have like a community, right? And it's obviously far away from super active and at least like in public channels, but we step by step trying to improve it. So in case you want to stay in touch, right, and maybe continue conversations that you started at this event, feel free to join our Slack channel. Just to show how it used to be in a bit more cozy atmosphere, where in this case, like Starlight hosted us. That's like where we were still able to meet in person and actually sit next to each other, like on a sofa with the strangers. But now this is like a picture from last event in March, actually. That's how it looked like on my side, at least. And you can see like a couple of speakers, right, and the streaming part. But that's basically things are changing. But we also hopefully learning something from that. So as I said, usually we aiming for a few speakers. Today we have only one, but we also experimenting with a different format of us having like a bit of like conversation afterwards. So stay tuned after the talk, and we're gonna have like hangout call that you can like go a bit more into conversational side, because I have a feeling that right now it's also like a moment when all of those communities have a bit of time to reinvent where is the value, right? Because if you just go for having like one video, I think it's like helpful. And with the speaker today, we definitely have very nice and entertaining talk, but it's a bit of missing this like a nice conversations that you have like after the talk, either it's like on a big stage or just like in a meetup, when it's not only like speaker and slides, but also community, and you can find something that you didn't even know you're going to talk about. So I'm definitely looking forward to this experiment. And since it's just experiment, we bear with us, because you never know how it's actually going to turn out and what results we're going to find there. So I'm really, on one hand, looking forward, on the other hand, like a bit of gonna see like how things are gonna roll out there. We also have this GitHub page where I'm still trying to put a bit more slides, but in case you wanna see those slides of the speakers, it's either follow the speakers on Twitter, and they're gonna share the handler of today's speaker, or try to go to the GitHub, and I will try to keep those updated and have a bit more information. So usually if you do like it in offline, there's like somebody who need to host us, right? And in offline setup, sometimes we're going to have like 150 to 200 people in the room. So it need to be like a bit bigger location. Now, funnily enough, right, with all limitations, we also have some freedom and democratization, essentially. So now it doesn't really matter how many people we're going to be, right? Because we can just sit like on the same sofas that you have at home, and you don't need to have like a big sponsorship, right? But if you feel like that you and your company would like to support this movement, I don't know, like maybe you want to have some virtual pizza or virtual beers, or just like support with anything else, right? Feel free to reach out to me, and we can definitely make you engage with this community that we have. Usually we also a bit more outlining the next events. Right now I don't really have like super specific, like next point for us, but as I said, sign up for Meetup, right, or subscribe for our page, or Twitter. It would be like a good communication channel to find what's up next. Yeah, and if you have some conference event that like friends of ours, we also mentioned like on this slide. Right now, I think conferences is also a bit more on yeah, like a bit of like reinventing themselves. There's like a good event from CodeMotion that also like becoming free, right? And there are like also some fellow GDs, as Margaret, as you know, Leigh. Also, she's going to be speaking there. So in case of that, feel free to reach out, and I'm going to share the links like on Slack or like elsewhere, basically. Yeah, that's more or less it from my side. The last thing to say is all community event, right? So in case you would like to share your big experience in a form of like long talk, or maybe something exciting that you were building during the this like lockdown times, feel free to also reach out, and it's super exciting to hear your lightning talk or even bigger one. In case you wanna, you're watching to this like stream, or you see our activities and you feel like, hey, these things that I definitely can improve, please approach me, and I'm more than happy to share responsibility, but also appreciation and visibility for you as well. So we can make the space a better community-driven event. Yeah, and that's more or less it. So next up is basically our amazing speaker. And what I would like to just mention last organizational piece, that since you're watching this like on YouTube, we also gonna have like your questions collected like on YouTube. So please write them there, and at the end of the talk, I would also bring these questions to the speaker. That's going to be like more on for first part, and after you can still have like a conversations like later on. But I guess like it's still pretty essential for you to write them down, so you're not gonna forget those questions on one hand, but also it's going to be like recorded, and for more broader communities, they're going to see it, and yeah, maybe find it like later on. Yeah, with that, I'm done with my part of sharing. So I would be slowly adding our amazing speaker. So now you're going to be like a part of the video stream.
Hello, everybody. My name is Leigh Johnson, and I'm tuning in or coming to you from San Francisco right now. We've been sheltering in place for about 3 months, so I'm pretty excited to finally do some events, and I'm really interested to see how this session goes. I haven't done any remote events yet, so please post your feedback. Let me know how the Prezzo goes so that we can improve these and kind of do some better audience engagement. We're all learning together today, which is the thesis of my talk today. I'm going to be telling y'all about some things that I learned while building a DIY CCTV with a Raspberry Pi and some TensorFlow models. And my goal for this project was to create a real-time object tracker. Yeah, and I'll walk you through how I did it. So first things first, let me walk you through what I'll be presenting today. I'll introduce myself and the project. You see it there on the right, fully built. I'll show you everything that I used to build it. I'll walk you through how I added TensorFlow models to the Raspberry Pi. And then I'll walk you through some of the control scheme for actuating the servo motors so that I can track a moving object with this pan tilt hat that you see in the picture on the right. And finally, I'll show you how to do some more or less one-click installation of the software I wrote, so you don't have to go through all of the learning that I did while setting this up. So quick way of intro. I'm Leigh, hi. And this model right here is 99% confident that I have a face and that my face sits inside the green box. I work at Slack, that's my day job. I was originally hired at Slack not as a machine learning engineer, which is what I do now, but as a database reliability engineer. It's kind of like a site reliability engineer, but laser focused on the data tier. And I created automation for and operated Slack's petabyte scale data store and cache fleet for roughly a year before the machine learning services team was formed, and I joined it in 2020. So right now at Slack, I work almost exclusively on natural language processing. My team builds machine learning APIs that empower other Slack engineers to build things that leverage NLP models without necessarily worrying about the data pipeline, service availability, or the nitty-gritty nuances of each modeling technique. I also am a Google Developer Expert in machine learning. So that's a program that recognizes contributors in the ML ecosystem. Most of my work for ML program focuses on deploying TensorFlow models to tiny single board computers like the Raspberry Pi or microcontrollers like Arduino. One thing I wanted to point out is I'm not a data scientist by training. I've actually been a systems administrator, a database administrator. I worked in video games for a while as a game developer. I made mobile apps, and I've been a data engineer. So with that varied background, I'm coming to you today with some things that I use to just teach myself the basics of computer vision. It's never been a role I've officially had at work. It's all stuff that I've taught myself, and I wanted to give you some of the tools and software that I wrote while going through this process myself. So above all the titles that I've had, I fundamentally identify as a maker. And on the right, you can actually see my birthday present to me. It's a Prusa 3D printer. I just assembled it myself. And the reason why I wanted to show it to you is because the assembly instructions came with these gummy bears. And you're supposed to lay the gummy bears out in order to visualize your progress through the assembly. And I opened the documentation and saw there were exactly a certain number of gummy bears in the documentation. And I was so surprised at first to open the package of gummy bears and find, oh my goodness, there were exactly as many gummy bears in the package as there were in the documentation. And then I realized, oh, they're Haribo gummy bears. They're German engineered. So then I was not so surprised that there were the exact number of gummy bears in the package. So fundamentally, I'm a maker. And I learn by making things. I learn by doing hands-on tutorials and writing hands-on tutorials for other people. Okay, so in this video, I'm going to be using a pre-trained face SSD model. Let me show you what we'll be building and going through today. I'm so sorry for the low quality of this video. It's shot from my dining table, which is where you see me shooting this video now. Let's see if I can get it to play. All right, there we go. Yeah. So what you're looking at is a pre-trained face SSD model. It's a type of single-shot convolutional network specialized in face detection. And the tracking motions you see are a pair of servos that control the pan, tilt, or XY motions of a Pi camera. It's attached to a Raspberry Pi. I wrote a proportional integral derivative controller to actuate the servos. You can kind of see me, keep looping through it. Kind of see me ducking behind a plant at some point in order to test out the PID controller for the servo motors. I'll walk you through how I built and coded all of this. Again, sorry for the kind of low quality video and the glare. Let's see. All right, so here are all the materials that you would need in order to build this yourself. The bare essentials are a Raspberry Pi. Now, if you've never heard of a Raspberry Pi, it's a single board computer that's really popular with hobbyists and makers. It runs Linux. The most popular Linux distribution for it is called Raspbian, which, as the name might imply to you, is a Debian derivative. So it uses a 32-bit kernel in user space, and the latest revision, this Raspberry Pi 4, actually contains a 64-bit ARM processor. So you can run 64-bit ARM distributions by Fedora, Arch, or Gentoo on the Pi, which comes up later during model optimization because some of the things that you can do with a 64-bit CPU are very interesting when thinking about on-device machine learning. The next component you'll need is a Raspberry Pi camera. So this is specifically created by the Raspberry Pi Foundation, especially for the Pi. It uses something called MMAL, which is a C library designed by Broadcom for use with the Raspberry Pi's GPU, which is what's processing all of the image input that you'll be working with in order to do all of these inferences. I'll walk you through how to sample frames from the buffer, not in C, but in Python. The other component here is a Pimoroni pan-tilt hat. There are 2 versions of it available. There's a self-assembly kit, and then you can buy kind of a fully made kit if you're looking to save a little time. At its essence, it's just a hat that sits on the Pi's GPIO pins and 2 servo motors, which actuate or which control the movement of the camera on X and Y coordinates, or actually X and Y angles. The other things you'll need are a micro SD card, which will hold the operating system for your Raspberry Pi. And I'd recommend getting some kind of a micro HDMI cable or HDMI cable so that you can see the output of all of this stuff. I run my Pis headless, but it's really helpful to be able to plug your Pi in and debug things. So even though I run headless, I still carry these cables everywhere with me too. Some other things that are optional, but super recommended, this thing right here. This is called the Coral Edge TPU USB Accelerator. It's an application-specific integrated circuit, or ASIC, that was designed by Google, especially for accelerating TensorFlow inferences. It only accelerates inferences, not training. And you can see on the right, the actual ASIC chip is kind of superimposed over a penny to give you an idea of how small it is. Although this is optional, if the goal is real-time detection in your project, as it was in mine, I would consider this essential for that. Without this, I was getting about maybe 6 frames per second. And with this, I was able to perform inferences and actuate the servo motors in real time. Or at about 24 FPS. So here's kind of a comparison of some of the ways that you can run TensorFlow on a single board computer or on these tiny microcontrollers. And you can see the benchmarks that were taken here against MobileNet and MobileNet v2. If you're just running the fat TensorFlow model on a Raspberry Pi, inferences can take more than half a second. If you convert the model to TF Lite and still use 32-bit like floating point representation, you can get down to about a quarter of a second per inference using MobileNet v1 and v2. If you add a Coral USB Accelerator, you're able to perform inferences faster than about 50 milliseconds, or fast enough to actuate a real-time controller. All right, so getting into some of the models and theory behind this. I like to call this section, I learned all of this, so you don't have to. I knew that I would want to start with a pre-trained model. And I knew that there was an entire ecosystem and garden of pre-trained models called the TensorFlow Model Garden. I got started on this project in December 2019. So the TensorFlow model repo contains a whole collection of official TensorFlow models divided into 3 categories. So the official models, and you'll want to use these if you can, are all written with TensorFlow 2.0 high-level APIs, so Keras. They are maintained by the TensorFlow team, and they're all state-of-the-art models. And they're kept up to date, they're supported, they're well documented, and they're reasonably optimized for fast performance while still being pretty easy to read. Unfortunately, the models that I wanted to use, which are very small and compact, optimized for mobile devices, MobileNet v2, Base SSD, were published by researchers. Now, the research category of the TensorFlow Model Garden is a collection of research model implementations in a mix of TensorFlow 1 and 2. They're not maintained and supported by the TensorFlow team, but by the researchers on kind of a best effort basis. And it's really cool that the researchers have published a lot of their research online and made it available so that you can reproduce some of the papers that they've written and use these state-of-the-art models. But sometimes this area can be a little hard to work with. It's not as well documented or supported because the TensorFlow team doesn't maintain it as well. And then there's the community section. So this is just a list of third-party repositories that have machine learning model implementations in them, and they're all powered by TensorFlow 2 as well. So firmly in the research category were the things that I wanted to use, which was this MobileNet v3 architecture that had a single-shot detector added onto it so that I could do multi-box object detection and multi-box bounding boxes using MobileNet v3's base architecture with Cocoa labels. I also wanted to later do a face detection library, and I knew that face SSD was fairly well optimized for performance on mobile. Unfortunately, all of the training code, the published artifacts, the checkpoints were all produced using TensorFlow 1 point something. And this was in December 2019, so too long ago. And I was firmly in the camp of wanting to publish TensorFlow 2.0 examples and use TensorFlow 2.0 in all of my future-facing projects. So I set out to go and figure out how to do this. So first, step 0. Here are the things that I had to work with. Just taking things from the model garden, these pre-made models. I had TensorFlow 1.0 training code. I had this frozen graph, and this represents the state of all variables at a certain time, so that I could do TF Lite inferencing with that frozen graph. This is kind of a legacy TF Lite format. So I knew I wanted to convert that to a more modern TF Lite format, which is backed by a flat buffer rather than this frozen graph format. I had a trained checkpoint to work with. And when I went to go inspect the actual model's layer architecture, I saw that this final Nonmax suppression layer had been removed. If you go and look at the papers for Face SSD or the SSD MobileNet papers, they talk a little bit about using NMS in order to take a lot of bounding box proposals and choose the best one. The model was also float 32 format, so it accepted float 32s as input and output float 32s as well, and expected to work with floating point representation. All model weights for floating point representation, same with the weights. All right, so here are my blockers. I need to re-add the NMS layer or implement it myself, one of those things. I need to convert everything to TensorFlow 2.0, and I knew I also wanted to quantize for the edge TPU. Quantizing means representing a model or input with fewer bits than the original representation. I wanted to go from floating point 32 representation to 8-bit integers. Okay, so I also wanted to avoid retraining the full network, since the researchers were most likely to know the nuances about the architecture. This was a side project for me, and I wanted to get something done in a weekend or two. And I figured that retraining the model could be an entire endeavor. After all, these researchers had dedicated many months and weeks in order to tuning the results, and I wasn't confident that I could reproduce the results quickly. So I really just wanted to convert this frozen variable graph to a flat buffer, which is the format used by TensorFlow's 2.0 TF Lite interpreters. I also wanted to add the Nonmax suppression layers cited in the research papers, which had been removed for transfer learning applications. It's pretty reasonable. Finally, I wanted to quantize the model's floating point weight representation to 8-bit integers so that I could accelerate these operations with my edge TPU, an ASIC specialized for doing TensorFlow operations, but only works on 8-bit representation. So I went into the TensorFlow models repo, and I found this, or rather, I wrote this. And what you're looking at here is a script called export tflite ssd graph.py. You can kind of see it at the very, very bottom. And this is a script provided by the researchers to create the frozen graph, that TensorFlow 1.0 TF Lite representation. The variable state gets loaded from the model checkpoint, which is also provided at the bottom. After reading through a lot of the code in the model zoo, I discovered that I could add the researcher's Nonmax suppression layer by re-exporting this graph with the add post-processing op flag, which you see is the very last line at the bottom. So after about 12 hours of reading through the repo, going through this code, I came up with a simple 20-line script. And that 20th line just adds the non-max suppression layer into the TF Lite frozen graph representation of this model. So now I had a frozen graph, which is that legacy TF Lite format, with the non-max suppression ops as the final output layer. Why did I have to go through all that trouble? So non-max suppression, again, is a technique for selecting the best bounding box from a number of box proposals. If I couldn't get the researchers' NMS implementation working, I'd have to write my own, which, while doable, would probably take me more than a weekend. So if you see on the left, before non-max suppression, the model's raw outputs a couple of bounding box proposals, and non-max suppression is a technique for choosing the one that best bounds your object after you've detected it. Okay, so oops. Here we go. Oops, sorry about that. Okay, step 2. Sorry about that, my internet's active. There's a little bit of latency for me as I switch through these slides. Okay, step 2. So now that I have the frozen graph, or TensorFlow Lite 1.0 representation, I need to convert that to a flat buffer. And I did this using TensorFlow's Toco build tool. So you can see as the input file, I have this tflite graph.pb file, which is the frozen graph representation, TensorFlow 1.0 representation. It outputs this tflite file, which is the TensorFlow 2.0 or flat buffer representation of the model. I specified my input shapes, which were just a 320 by 320 square with 3 channels for RGB. And I added this output array of post-processing operations that represent the non-max suppression layer implemented by TensorFlow researchers. I said I'm going to use float as my inference type, just as a test. The model published weights and was trained with floating point representation. So I wanted to see if I could get it working with floating point representation before trying to quantize it or convert it to integer representation. And to give you a little bit more info about this detection post-process up, you can see this definition for it here. And you can see some of the inputs are the raw box encodings and class predictions that are output by any type of SSD architecture. And then the outputs of this layer, after applying an NMS op, are the best bounding box proposal per class instance, along with top left anchors as well. So this is exactly what I needed, and I had the means to get it, so I did. Okay, after I got that working and tested it out of my Pi, I then quantized the model representation. I also used Toco for this, and I also used the frozen graph representation with the model weights loaded from a checkpoint and output it to the TensorFlow 2.0 flat buffer. And you can see here, a lot of these parameters are the same. The one that I want to highlight is this inference type, where I've gone to a Quantize uint8 inference type. As a result of quantizing the space, you also have to provide the mean and standard deviation values. This is a type of normalization operation. If you go from a floating point representation to integer, you have to specify what the center of your transformation is going to be. So for me, I just centered these at 128. The reason why I'm using that is half of 256, which is the all RGB values. Let's see. The other thing that's interesting about these are the allow custom ops flag, which is not enabled by default. So that's necessary to add these post-processing layers, or if you write your own post-processing layers, either in C++ using the Edge TPU, or even, you would need to supply this flag. Okay, so I did it. I had a model with the Nonmax suppression layer. It was usable with TensorFlow 2.0, and I had quantized it for the Edge TPU. I needed to quantize and use the flat buffer representation so that I could accelerate inferences with the Edge TPU. If you're like me and enjoy hands-on applications to learn, I have another starter project for you that you might be interested in before you try the full pan-tilt setup. At this point, I had to pause to go back through some computer vision theory, and I ended up writing another tutorial based on what I learned. So I covered the fundamentals of convolutional neural network architecture, which is widely used for computer vision applications. The face SSD and SSD mobile networks that you see are fundamentally convolutional neural networks that have single-shot detection added. The starter project is just an image classifier. So rather than detecting objects and proposing bounding boxes, this just accepts an image as input and outputs the classes for that image. I also have some visualizations of a convolution operation because I learn best by visualizing things with Post-it notes. That's a Medium article in the Bitly link, so if you want to go through that later, I've got that. The last interesting piece of this project is how to actually control the servo. So what you're looking at is called a proportional integral derivative controller. And this is a type of feedback loop that attempts to reach an optimal value. It's powered by a simple error function, and it takes the XY camera frame center and subtracts the centroid of a bounding box. And that value is equivalent to error. If you look at the image on the right, if the camera's frame were the red box, then subtracting the center or centroid of the proposed box would put the error right about at that line into my belly button. So this is a type of algorithm that's used to calculate the next XY coordinate based on a current error value, some of your historical error values, and then it'll anticipate future error in order to dampen any overcompensating movement. It's used in a lot of industrial control systems in order to actuate servo movement. It's also used in flow control if you need to control flow of fluids. So this is a very kind of traditional control mechanism, and I knew it would be the exactly right algorithm to implement in order to control two servo motors on opposite axes. Okay, let me go through some of the math behind this. I think I'm probably running out of time, and I want to get to questions because those are the most interesting part. So at a bird's eye view, what you're looking at is the scrolling math of a mad woman. But I want to point out just in the top right corner some of the components of this algorithm. The P in proportional, or the P stands for proportional, and it's proportional to the current error. So at any point in time, this value is equivalent to the distance of the camera's center to the center of a bounding box that's proposed by a model's inference routine. So this is always proportional to your error. If your camera is centered exactly over the centroid of the bounding box, its value is 0. It almost never is. I sample and calculate the error at about 24 FPS. This is why it was so critical to get a model working that could do inferences in under about 50 milliseconds. Otherwise, the rate at which I could sample and calculate my error wouldn't be fast enough to actuate the motors so that they could track me. All right, the next part of this algorithm or formula or calculation is this integral. And this is the integral of all historical error values. And these are calculated over time, so they're integrated over time. less significant corrections reduce the error. If the error is eliminated entirely, this term doesn't grow anymore, so the delta becomes 0. The last component is this derivative calculation. This is what will anticipate future error. And you can see it's the derivative over time, so it has a dampening effect that prevents overshooting. If either the p-value or the I-value cause overshooting, this will dampen before getting to the final output, which is just the sum of all these values. So all of these terms together create a feedback loop that actuates the angular motions of the X and Y servos in this pan-tilt software. So those are all things I learned, so you don't have to. Let's get to the cool part, how to actually put it all together. I did a detailed hardware and software installation in a blog post. So this is long form, it's beginner friendly, it's on Medium, and you can go check it out in this bit.ly link. It assumes that you've never done anything with the Raspberry Pi. We all have to start somewhere. So it includes some pictures and images about how to install things like the camera on your Raspberry Pi. And I tend to defer to the experts on this. So it'll walk you through installing an operating system for the first time. If you've never done anything with Linux, I defer to Raspbian's install in order to walk you through that kind of stuff. And then after you've got the Raspberry Pi all set up, I've created a package that you can just pip install. So you can just pip install RPI Deep Pan Tilt and have all of these models, this software, this camera control installed automatically for you. So it's a little bit easier than what I had to do, I think. After you install everything, you get a command line utility that looks a lot like this. So the usage is you run RPI Deep Pan Tilt, and I've got a couple of different commands. This one is the track command. So you can track some kind of a label. I provide examples for face tracking. There's also support for tracking every Cocoa label that's in the SSD MobileNet v3 model. You can list out the supported labels as well with this command line utility in order to see what you can track or what you cannot track. And these are meant to just be end-to-end examples of how you might develop a CLI entry point for a model that in real time performs inferences on device on the Raspberry Pi and then actuates some servo motors using GPIO controls. So the coolest part about all of this is other people have taken my work and actually gone and done things in the wild. This is a more refined build of anything that I've done. And this does automated face recognition, tracking, and fever detection using a custom model. It also detects masked faces as well to try to identify people that are sick in response to the whole COVID-19 thing. And it was created by Martin Kim. You can follow him on Twitter. This is very cool. And here it is. So there's the pan tilt setup you have there. He's using an MLX 9640, which is a type of IR and thermal array that you can hook up to a Raspberry Pi. And yeah, you can see it is tracking his face. And the thermal array also provides a heat map per pixel, interpolated, I believe. And I think that's about all I've got for today. I have a CLI entry point for all of this. You can just run RPI Deep Pan Tilt commands on the command line. There's a developer API coming in 2.0, so people like Martin or you can just import some of the work that I've done and start writing software immediately. Check out the GitHub repo for updates. Just star it. I'm actively maintaining it. I actually just shipped a release this past weekend that closed a lot of issues opened by users. So if you want to engage with the project and follow it, I'd love to hear how you're going to use it. I think it's really cool that people are going out and building their own things with us. That's it. That's all I've got. I will open the floor for questions now.
So first of all, thank you for an amazing presentation. It's like really cool starting from like hardware and after going like all the way into like all cool things that you found there. So definitely nice. I've got a couple of questions. I guess me saying that they're going to be like hangout call is also made people even more, hold the questions for later, but I definitely got some of the questions. So one is you showed your, migration with Docker, right? So basically you were transferring like a TensorFlow model to TF Lite model, and you were using it like all in command line. So the question is like, can you use also Python for that, right? So can you write all of those like parameters? Is it like feature complete for that? Or you have to use basically, command line and all of those parameters?
For the conversion that I needed to do, which is to go from a TensorFlow 1.0 frozen graph to the TF Lite flat buffer representation, I did need to use Toco at that time. I'm not sure if the utilities have been updated to support this path in the last 4 or 5 months. An alternate path would have been to take the TensorFlow 1.0 training code, convert it to TensorFlow 2.0, retrain, and then you could use the TF Lite converter in order to convert that representation in order to a flat buffer. So there are a couple of options for converting, and I chose the one that didn't involve retraining the entire network.
Yeah, makes sense. Cool. Another question would be, since you're coming from ops background or engineering background, what would your recommendation of CI for such a project, right? Because I get it works pretty easy for now, right?
Yeah, I love this question. The TLDR is I build and release all of this software on my own Raspberry Pis. And I was actually thinking about, since I have a 3D printer now, racking like 12 Raspberry Pis in a build cluster. This isn't great because self-managed CI is, well, just another thing to maintain, right? It's another thing screaming at you. Travis recently set up ARM32 support as part of their build processes. Previously, it was only ARM64. I haven't tried it out yet, but I will let you know. And if I get it working, I'll put an example implementation in RPI deep pan tilt. I plan on testing against 32-bit ARM forever, just because that's the default representation that Raspbian chooses to use. Even though the Raspberry Pi can support 64-bit, has a 64-bit processor, Raspbian hasn't updated the user space to run 64-bit programs. So unless you install an alternate platform, you basically can't do ARM64. In summary, you have to set up your own Raspberry Pi architecture. But if there is a Travis way to do the CI, I'll put an example at RPI deep pan tilt.
And let's say if you build it already, because like one part is the packaging, right? Another one would be actually pushing it to actual device, right? What is like any tricks to actually get it propagated there automatically? Imagine you have this like camera stain in your, I don't know, like where you use it basically, right? What would be like a good deployment of or release rollout basically of that?
Yeah, I test everything manually. It's kind of the not so secret about a lot of software we make is if the expense of testing exceeds like the cost of writing testing, just do the bare minimum in order to validate that it works. Once I start implementing developer APIs, those are going to be harnessed with much tighter unit tests, right? Because those are APIs and I want to validate that nothing has changed unexpectedly each time. But my test process right now is to basically just build from scratch a lot of this software, try to reinstall it on a fresh installation of Raspbian, and if everything works okay, I'll cut a full release and upload it to PyPy. I do have some automated processes around standing up my Raspberry Pis. I like to treat them as immutable infrastructure, but they're not generic enough for me to give to you yet. I'm ex-Ansible, so I use Ansible playbooks for everything.
Yeah, cool, awesome. That's a really good answer. Another one is again around Python and Raspberry Pi. Did you see like any bottlenecks because of Python, or did you try TF Lite C API to actually run it maybe more efficiently, or maybe it's not even an issue for that basically?
Yeah, definitely. So the actual process manager routine is limited by being implemented in Python, even by making decisions about actuating the X and Y axis in independent Python processes and sharing some memory space for values. There are restrictions and communication overhead between two Python processes. Being limited by the GIL for this type of real-time application is tricky. I would have preferred to do a C++ implementation, but the Edge TPU only ships a Python-based runtime right now that works on the Raspberry Pi. The Edge TPU library is not fully open source. They ship a shared object that's built against some arbitrary revision of TensorFlow. So I decided to just use their TensorFlow Lite runtime, which is actually a binary wheel that you install in Python, and it includes their own implementation for the interpreter and delegate classes that you'll find in TF Lite. What these do is the interpreter is a method for setting up a TF Lite interpreter and kind of controlling the memory that it owns. And then the delegate is an abstraction that registers a kernel node in TensorFlow and parses a TensorFlow graph to pull out operations that it knows how to handle and accelerate. And all of that is in TensorFlow, and you're supposed to utilize these APIs to write your own delegates, and the Edge TPU actually ships their own base classes. So I needed to use those, if that makes sense.
Yeah, definitely. Like, it's very nice. And I also tried a bit of like this Edge TPU, so definitely I've seen those like delegates, and if you can extend them. And actually, speaking of that, like last question from my side would be, what was your experience with Edge TPU? Let's say if you would, I don't know, need to add like some additional operations, right? Because you added like a Nonmax suppression, right, and other ones. How easy it is, right? Because I know they're like on their website, they're putting some examples of already convert models, right? But if you would need to have something custom, right, is it easy and walk in a park, or is it a bit more like complicated? What is your experience so far?
I haven't tried it yet. I expect it's not going to be straightforward, but I've also found that the communication from the Edge TPU team is pretty good. I opened an issue in their GitHub and I received a response within like 12 or 16 hours. So for someone just working on a hobbyist side project, that type of response came cool. Very good. Yeah. I would love, the thing that's blocking me the most on that project is getting the full open source for the Edge TPU library so that I could just compile it against any arbitrary revision of TensorFlow. I'm not sure what they're doing to sort that out, whether they're choosing not to compile against TensorFlow or doing a different type of build process. So I'd be interested to see that development, and I'm following it pretty closely.
Yeah, nice. And I've seen also that the release cycle is also pretty active, right? So every now and then you can see new versions of Python, right? And all bugs were fixed. Because, for instance, before, like Mac was not really supported like out of the box, right? And now you can also run inference like on Mac as well. So you can just test it, out of the box.
That's really cool. Right on.
Yeah, awesome. I guess that's more or less all questions that people want to try to ask. So my suggestion would be that we have like 5 minutes break, and after we continue like on a hangout when other people can actually join in and ask it in person. Thank you again for amazing talk. There is actually like last question popping up because it seems like we were a bit of a delayed. So I now can just like leave them hanging. So Matthias is asking, have you tried to utilize onboard GPU on Raspberry Pi 4?
For accelerating TensorFlow operations? No. So just about everything you see is CPU only, accelerated by the Edge TPU if present. I'm not sure how that would work. I'll see what I can do or if it's possible. Yeah. No, I've never tried it. If you have, I want to talk to you.
So Matthias, you can reach out on Twitter, and I guess like we can figure out how it works, or on GitHub, right? Because maybe it's even easier if he sends a pull request, right? And suddenly it works even better on on GPU on Raspberry Pi 4. Cool. And another question is, what is the next TensorFlow plus HTPU project? Is there anything exciting that you're planning for?
That's a good one. So I'm moving over from computer vision to voice detection using a respeaker. And what I want to do is create something that can, in real time, provide captioning with just a tiny on-device, like a little TFT screen, and do completely on-device inferencing for either live captioning or live translation. Very similar to what you see with the Google Translate project, or if you turn on live captioning for anything in I think Google Hangouts supports this now, or something related to the Google Docs Prezo. So I'm going to try to reproduce that just using on-device Raspberry Pi.
Nice, cool. So I guess if you're interested in this speech projects, you can also follow Leigh on Twitter and also on GitHub. So things are going to be also popping up there like every now and then. Great. Thank you again for the nice presentation. And I will just share the link also here in comments on YouTube and share it to you. So potentially like in whatever, like 5 minutes break, right? Or 10 minutes break, we can continue there with whoever want to have this after talk conversations. That's usually pretty valuable. Thank you.
Sounds good. I'll see you in 5.
See you in 5.